Good afternoon. Today we will discuss analysis of variance. Popularly known as ANOVA. In last class, we have discussed about the difference between two population means, and in hypothesis testing we have covered the equality of population means from univariate point of view, from multivariate point of view. So, if we just recapitulate this, what we will find out that one is number of population, then your number of variables, then hypothesis, then the techniques used. What technique is used? If you say number of population L, number of variable P and hypothesis as usual, then the situation is single population L equal to 1. Suppose number of variable is also 1, P equal to 1. What we do in hypothesis testing? We do H0 mu equal to mu 0 and H1 mu not equal to mu 0. Generally we test this, and we use for the small sample case t test. We assume that population is normal. Now, L can be 1 and P can be more than 2 all case also, that is single population more than or equal to 2 variables, and your hypothesis will be again H0 mu equal to mu 0, here mu is a vector quantity, and H1 mu not equal to mu 0, and we have used Hotelling's t square for hypothesis testing, again for small sample case. Now, second issue we have discussed L equal to 2 population case. Under this also we have already discussed P equal to 1 case, and there our hypothesis was mu L equal to mu m, and alternative hypothesis we have framed as mu L not equal to mu m for at least one pair, and we have used t test. And for P greater than equal to 2 case, we have hypothesis like this, that mu L equal to mu m, here mu and L and mu m are vector quantity, and H1 mu L not equal to mu m for at least one pair, and we also used Hotelling's t square. Okay. So, this is what from hypothesis testing point of view we have already completed. What will happen when L is 3 or more? So, our discussion today for L greater than equal to 3 case, where L stand for population, that is number of population. Okay. So, in this case we will first consider the univariate issue, that means we are interested in P equal to 1 case, and when we test equality of several population means for one response variable, the technique used is ANOVA, analysis of variance. So, that means what I said, that suppose your case is P equal to 1, that is univariate case, there are several groups or population which is definitely 3 or more. In that case, the first the t test is not applicable. Simultaneously, if you want to test the difference, you require to use a special technique known as analysis of variance. So, today we will see in terms of ANOVA. For ANOVA, these are the contents: conceptual model, assumptions, estimation of parameters, model adequacy tests, interpretation of results, followed by references. What is this conceptual model? I will be describing with an example. You see this slide here, we have three processes A, B and C. These three processes are producing, let steel washers. So, our product is steel washers. Steel washer is the product, which can be in two dimensional figure, we can see like this. Suppose this is the case, and then this part, or other way, this inner circle part, if we consider, this is ID, inner diameter, and if you consider the outer circle, this will be OD, which is outer diameter. Let both are measured in millimeter. Millimeter is the case. Here these values are in millimeter for outer diameter. The problem is that you are producing through three different processes, but you are producing same thing, that is steel washer, and outer diameter is the quality variable and which is specified by the customers. Okay. Now, as a manufacturer of these steel washers, what you require to know? You require to know that whether all the processes are producing at the same level from quality point of view, same level or not. And the manufacturer is interested to test the differences in means of outer diameter for the three processes. So, our objective here is, are there mean differences in outer diameter of the washers produced by any two of the three processes. Okay. Under such situation, the most widely used graphical plot is box plot. Okay. Now, see what is box plot. This figure shows box plot. This box plot is for process A, this is for process B and process C. In the box plot, there is one box and two whiskers. This one is box, the upper portion, this line is right whiskers and this is the left whisker. This box is determined by interquartile range IQR, and the horizontal middle line here, this is the median position from the data, and the circle plus 1, that is the mean position. Okay. So, if we see the three boxes here for process B and process A as well as process C, what we will find out that the box hardly differs in terms of variability except process C, but it is to be proven that whether this variability is different from A or B or not, apparently it is different. Okay. But if you see the mean point, the circle plus point, this one is quite different. Apparently, it shows that there is mean difference. You see, this is the mean point for process A, this is mean point for process B, this one is mean point for process C, and if I see the value, it is 20 point something, this one is around 18 and this one is again 20 point something. So, even if there is no difference between maybe process A means versus process C means, but there is chance that both process A and C means are different from process B, which is basically from the graphical plot it resembles like this. But what you want a quantitative explanation of this, and if we are able to do this, then we are able to answer this question, are there mean differences in OD of the washers produced by this. Then we will use, I told that ANOVA uses two hypotheses, one is null hypothesis and alternative hypothesis. What null hypothesis says? Null hypothesis says that there is no mean difference. As we have taken three processes A, B and C, so we are saying that process A mean as mu1, process B as mu2 and process C as mu3, and there is no difference means mu1 equal to mu2 equal to mu3. And our alternative hypothesis is at least one of the pairs, that means either mu1 mu2 pair or mu1 mu3 pair or mu2 mu3 pair is different, that means are different. So, pictorially the left hand side figure is your null hypothesis, and here the right hand side is your alternative hypothesis. If your situation is as the left hand side figure, you see what happened here. There is one parameter mu, please see the left hand side, this is mu here. This mu is the grand mean, grand mean. So, there is one parameter called mu which is known as grand mean. By grand mean what do we mean? By grand mean we mean that you have three processes here in this case. So, you have produced several items, you have measured the outer diameter in this case. Irrespective of the process, you take everything as a whole and compute the mean. Okay. This is what is grand mean, the totality. For example, in this case we have seen that we have will collect certain amount of data, and we have collected 10 data points, sample size is 10 for process A, process B and process C, 10 each. So, what will happen ultimately, total data point if I say n, that is 30, and you are considering every data points, all sum. So, sum of all the data points divided by 30, that is your grand mean. If you collect 30 data points, 10 from each of the processes, that will become your grand mean. Okay. Now, there is another mean which is known as process mean, or in this case we will say the population mean, because we have assumed that each of the processes are different, as if each of the processes are representing a population. Process A is one population, process B is another, process C is the other one. Mu1 is the mean of process A, mu2 is the mean of process B, and mu3 is the mean of process C. When null hypothesis is true, that means mu1 equal to mu2 equal to mu3, then it will be equal to mu. Okay, because we are you are collecting here 10 samples from each of the population, and when null hypothesis is true, what will happen? You compute the process A mean, process B mean, process C mean, you will be also the grand mean, you will be finding that they are equal, because it is obvious. Because what is the group mean calculation? Do you know that? I think all of you know N1 F1 plus N2 F2 plus N3 F3 by N1 plus N2 plus N3, that is the group mean. Okay. If you calculate group mean, this is the formula. where for the first case frequency is f1, second case frequency is this is basically f1, okay. N1 f1, N2 f2, N3 f3, and N1 is the number of cases from the, that is the, I think we have to use mu here, N1 into mu plus N2 f1 is, it is basically mu 1 mu 2, that will be better. So, I will write like this, N1 mu 1 plus N2 mu 2 plus N3 mu 3 by N1 plus N2 plus N3. Okay. So, this is the general expression we will not consider, we will consider this one here. So, if mu 1, mu 2 and mu 3 are same, then what is happening here? Then it is mu N1 plus N2 plus N3 by N1 plus N2 plus N3. This will be cancelled out, this is mu equal to mu. So, grand mean will be like this. Now, let us see that what are the other parameters available here. You see the left hand side again, there is another parameter which is epsilon IL, this one. This is the error quantity. Error in the sense, if you take any observation xi1 for the first process, from the first process, then if we consider that mu 1 equal to mu, then mu 1 will come here, the difference between the two, that the observed value minus the mean value, that is epsilon IL. Later on we will see this is basically error quantity. So, similarly for mu 2 also epsilon I2, for mu 3, that is process C case also epsilon I3 you are getting. Now, come to the right hand side. In the right hand side what is happening, what this figure resembles that the mu 1, mu 2 and mu 3 are not same. So, they are not coinciding with mu, and as a result what will happen, you will be getting one more parameter here, that is known as tau. You see this is tau, this one is also tau, this is tau. So, tau 1 is this value. What is this? This is the process mean minus grand mean, and tau 2 is again the process mean minus grand mean for process B. Tau 3 is process mean minus grand mean for process C. So, one more parameter is coming into picture. So, what we will do, using all those things, we will redefine the ANOVA model, and that is that any observation can be partitioned into three parts, that is xil is the observation, that is the ith observation on the nth population to be collected, mu is the grand mean, tau l is the population effect, and epsilon IL is the error term, which is not captured either through grand mean or tau l, or combiningly it is not captured basically. Okay. So, and what is tau l? Tau l is the population effect. So, nth population effect is tau l, which is also known as treatment effect. So, this is mu l minus mu, that means the mean of nth population minus grand mean, and other one epsilon IL, that is the error part, is calculated like this. Here we, this right hand side, there are two conditions given, one is L equal to 1 to L tau I L equal to 0 for equal sample size case, means when you collect sample, same sample size sample from the three populations or L population, what will happen here, you will find out that their effect will be, total effect will be 0, and one is more than the other. Some cases, some are more than the mean grand mean, some are less than the grand mean, but the total effect will be 0. And if you go for unequal sample size, then your formula will be like this, L equal to 1 to L, N L tau L equal to 0. Okay. I think let me repeat this. What we are saying in ANOVA case, we are saying that you have number of observations in this case, here it is number of population. Okay. So, you may find out that several population and also here will be several observations. Suppose I am saying that one observation is XIL, that is the general observation. That means ith observation on the nth population. This is my nth population. What we are saying further, that XIL, it can be decomposed as grand mean plus your population effect plus some error quantity. How do you get it? We will get it like by this manner. XIL equal to, I can write mu plus, let me write like this, mu L minus mu. So, mu cancelled out, mu L is there, but left hand side is XIL. So, XIL minus mu L. See, mu and mu will be cancelled out, mu L will be cancelled out. So, XIL equal to XIL. So, this is what is known as partitioning observation into three components here. One is grand mean, other one is the tau L, that is the population effect, and this one is epsilon I L. So, you are partitioning the observation values into three component here, and each component is a parameter of ANOVA. That is, from conceptual point of view, that there are three parameters, one is mu, another one is tau L and error component. Three things are there. Okay. If this is the case, then your hypothesis can be changed to H0, that is mu L tau L equal to mu L minus mu equal to 0, and H1 tau L not equal to 0 for at least 1 L. For at least 1 L. Like other multivariate models, ANOVA comes under univariate model. Like other multivariate model or like any model, any statistical model, that ANOVA also requires certain assumptions to be satisfied. These assumptions are populations variances are equal. So, you are sampling from L populations. The population variances must be equal. That means, what I mean to say, sigma 1 square equal to sigma 2 square equal to sigma L square. Okay, this to be satisfied. This is our first assumption, assumption 1. Assumption 2 is errors are normally distributed. What is this error? You have seen earlier that we have said that epsilon I L equal to x I L minus mu L. If you estimate this, this will be like this. So, this error quantity is normally distributed. Errors are IID, mean independent and identically distributed. If I say error 1 is normally distributed, then error n also normally distributed, that is identically distributed. Independent means there is no correlation between the errors. Okay. So, normal distribution as well as IID condition, those things you know, and how to test the normality we have also discussed earlier in some lectures. Now, I will first explain how to test the equality of population variances. If the this one is not satisfied, this assumption 1, that is equality of population variances, are not satisfied, what will happen then? You cannot use the traditional ANOVA. Okay, it is there, some other methods are there, but you have to go for different way of doing things, but here this assumption is vital for us. So, for equality of population variances, you will use Bartlett test. Bartlett test. Okay. Now, see the format what we have written here: hypothesis, statistic and decision, and that you have seen earlier also. Okay. Now, what is our hypothesis? That there is no differences in the population variances, and alternative hypothesis is at least one pair of variances are different. Okay. Now, here Bartlett proposed one statistic which is 2.3026 q by c. This is a statistic where q is n minus L log 10 sp square minus L equal to 1 to L n L minus 1 log 10 S L square. I hope you can recollect what is sp square and what is S L square. Okay. This is pooled variance and this one is individual population variance. So, you require to compute first L1, S1, S2 square, S1 3 square, S4 square like the all individual population variance values. Then also you require to compute the pooled one. This pooled one is given in this equation sp square equal to L equal to 1 to capital L n L minus 1 S L square by n minus L. I think that you have already seen in last class. What we are saying that sp square, this is n 1 minus 1 S 1, n 2 minus 1 S 2 like this n L minus 1 S L divided by n 1 plus n 2 up to n L minus the how many populations are there, that is L. So, this quantity is nothing but n L minus 1 S L, L equal to 1 to L divided by sum total of n L minus L, where L equal to 1 to capital L. So, this is your sp square you have developed earlier also. If you know this, then you are in a position to calculate q. What is capital N here? Which one? N minus L minus L. This capital N is nothing but this one. Capital N is L equal to 1 to capital L small n L. That means the total sample size from all the population. Although it is total sample size is not that meaningful, mean from every population you collected certain sample of size, some sizes, and that totality we are talking about. Then you have to compute C. C is 1 plus 1 by 3 L minus 1, L equal to 1 to L, n L minus 1 inverse minus n minus L inverse. This is your C value. Okay. So, please go through this C. There are basically C is another quantity which is basically L and n values are depicting this C, and this C will be used as the divisor. So, then chi square is 2.3026 q by C. So, given data set you have to calculate q, you have to calculate C, then you find out the chi square value. Chi square is 2.3026 q by C, and what does it mean when you say chi square? Because this quantity follows chi square distribution, and what will be the degrees of freedom? that you see it is clearly written here in the decision case that reject H0 when the chi-square computed is greater than chi-square L minus 1 for a particular alpha value. So, what do we mean then? That 2.3026 q by c follows chi-square distribution with L minus 1 degrees of freedom, correct. I think the similar thing you have seen earlier also, we are repeating. See the same problem. So, we have 30 observations, 10 from each of the processes, and what we have done here, we have calculated the variance for the first process, that is 1.51, variance for the second process, that is 1.43, variance for the third process, that is 0.93, and then you have computed chi-square by that is this one is chi-square. So, you have computed first pooled variance, then q, then c, then chi-square, which is 0.25. Now, we all know that chi-square with 2 degrees of freedom and alpha equal to 0.05, this value is 5.99. We have seen this one earlier also. Now, the computed value is less than the tabulated value. So, what will be your decision? You will accept null hypothesis or reject null hypothesis? Accept null hypothesis. You fail to reject null hypothesis. So, the same principle, this is my chi-square, suppose this is your chi-square distribution, your alpha tabulated value here, this is 5.99, but your value is how much? 0.25, it is very close to 0. So, what does it signify? It signifies that there is no population variance differences, all the population variances are equal, same. So, we are fit for ANOVA case. Okay. In ANOVA, it will not go in the same manner like Hotelling T square or your other one, that T test, the way we have developed. In ANOVA, it is a different ball game altogether, because here the primary concern is partitioning the observation. We have seen earlier, I told you that from the population point of view, when I am planning to collect some data, let x I l, this is the observation to be collected from a population where the grand mean is mu and population mean is mu l, then we have partitioned the observation like this. You have seen this one, see left hand side and right hand side both are same. Now, you have collected data, that means you have a fixed value now x I l. So, you have to go by sample grand mean plus your population mean minus again grand mean plus x I l that value minus population sample mean, not population, sample mean. So, it is okay. Now, you do little manipulation, x I l minus x bar equal to x l bar minus x bar plus x I l minus x l bar, square the term. If you square it, x I l minus x bar square equal to x l bar minus x bar square plus 2 into x l bar minus x bar into x I l minus x l bar plus x I l minus x l bar square, fine. You take summation over I. Okay. So, I equal to 1 to n. We are assuming that equal size samples are collected from the L populations. So, again I equal to 1 to n, then this side will be I equal to 1 to n, this side will be I equal to 1 to n. Now, what will happen to this middle one? The middle one will become 0, getting me, because of this quantity. So, when you write down sum total I equal to 1 to n sum x I L, this will be n x L bar minus x L bar for n times, that will be also n x L bar. So, this value will become 0. So, your resultant quantity will be I equal to 1 to n x L bar minus x bar square plus I equal to 1 to n x I L minus x L bar square. Okay. Now, see that this one, this is in the left hand side some quantity, right hand side also some quantity, 2 squares is given here. Okay. Achha, this is for a particular population, L population, yes or no? Because we have taken x I L, everywhere L is there, but how many L populations are there? Capital L populations are there. So, that means your observation is spreaded over all L populations. So, if I take one more summation, what will happen? What you will do then? You will write down L equal to 1 to capital L, sum total of I equal to 1 to n x I L minus x bar square equal to L equal to 1 to capital L, I equal to 1 to n x L bar minus x bar plus sum total of L equal to 1 to capital L, I equal to 1 to n x I L minus x L bar square, this is also square. Now, in this case, is there any I x L bar minus x bar, there is no I component. So, that means the same component for n times. So, you can write like this, L equal to 1 to capital L, n will be there x L bar minus x bar square plus sum total L equal to 1 to capital L, I equal to 1 to n x I L minus x bar square. Okay. So, what will be the left hand side and right hand side? If you see, when we calculate the variance, what we will do? We will subtract the mean value from all the observed values and then square it, and then we divide it by the degrees of freedom. Here we have not divided it into degrees of freedom, but actually what is happening here, this x I L minus x bar, this was the variability is this square. So, for all the observation case you have subtracted by the grand sample average. So, this quantity is known as sum square total. Okay. You see here that L equal to 1 to L, this I equal to 1 to L x I L minus x bar square, this is the sum square total, and we have already seen that other one n into L equal to 1 to L x L minus x bar square. This is what is the difference, the variability part from grand mean to the individual population means. That sum you have taken. You see this one, what you have done here, XL bar, this is the population for Lth population sample average, and X bar is the grand sample average, the difference between the two, and then these observations you have squared. So, if there is no difference between the population means, we assume that the sample average also will become same and it will be equal to the grand sample average. So, then this quantity will become 0. So, if there is any variability, this is because of the variability between the population. So, that is why this quantity is known as SSB, and we have seen earlier also XIL minus XL bar, this is nothing but the error part, which is not explained by the which is not explained by SSB. So, this is SSE, sum square error. Now, sum square total is equal to sum square between populations plus sum square error. So, what is happening here then? We are basically dividing the total variability in terms of sum square total equal to variability explained by the population plus variability not explained by the population, correct. So, this is the known as decomposition of decompositioning the total variability into between population variability and error variability. Okay. So, now we have to see the degree of freedom part, degree of freedom. So, when we compute SST, what we require basically? We require X bar. So, there are total n observation and we have sacrificed 1 to calculate our this one X bar. So, degree of freedom for SST is n minus capital N minus 1, where capital N is n into L when you sample from L population and sample size is equal. If sample size is unequal, then this will be your L equal to 1 to capital N NL, getting me. So, this is for equation for the equal sample size case, this is the equation for computing capital N for the unequal sample size case. Now, come to the between sum square. Now, under in between sum square, how many labels you have? If you see the computation, what you will be finding out? You will be finding out that population 1 to population L, and you will be computing here that bar XL bar. So, here X1 bar, X2 bar like XL bar, and then you find out the X bar. And if you see the computation of SSB, you are finding out that this is nothing but XL bar minus X bar square and then multiplied by n and that summation. So, that means essentially you are using XL bar. So, as there are L populations and there is relationship also with the individual population mean vis-a-vis grand mean. So, 1 degree you are losing here, and as a result you have total L data points and 1 degree is lost by computing X bar grand mean. So, plus n minus L, because this is the rule that the total variability will also be decomposed into the component degrees of freedom. So, total degrees of freedom is n minus 1 and your SSB's degrees of freedom L minus 1, SSE's degrees of freedom n minus L. So, if you make a sum L minus 1 plus n minus L, it is nothing but n minus 1, right hand side, n minus L plus L minus 1, sum total will be n minus 1 and which is equal to this. Keep in mind this one.
Can you find out this n minus L from that previous equation?
Which one?
This last, last right, from here can we find out that the degree of freedom from
Yes, you are finding out, no? What you are using, you are using L populations. So, you have L mean values.
this is okay. This is right hand, the second part.
Second one, what is happening, n into L, this is the total observations. So, we are talking about n equal to small n into L, this is the total observation. This side is reflecting the total observation is this, but you have already computed x bar. So,
This is also okay. This portion.
this one,
This portion.
this portion, see how many Excel you have computed,
Excel
bar,
Excel bar is the
L
number of
population. So, total is n minus L. Okay. So, there is L Excel bar. To compute this one, you require to know all those Excel bars. So, already L degrees of freedom you have lost, you have capital N degrees of observations, L is lost. So, n minus L. So, this is what is the decompositioning the degree of freedom, correct. This total concept, whatever we have discussed so far, can be seen in a table which is known as ANOVA table. Whenever you go through any textbook on ANOVA or any software you use for ANOVA, what will happen, you will be finding out that one table will be formulated and this table is known as ANOVA table, which is very popular table. Later on, even in regression other cases also we will be using ANOVA table. This ANOVA table, for the problem we have considered now, there are few items. One is sources of variation, then the sum square, what we have calculated SST and SSB, all those things. Degrees of freedom also you have seen. Then you have to compute mean square, you have to compute F value, then based on F value you will be accepting or rejecting the null hypothesis. Okay. So, we have considered L population, no other factors we have considered in the present case. So, sources of variation is the different populations, and apart from this you cannot nullify the random effect. So, random effect is coming under error. So, another source of variability is error, and this population and error, these two sources are making the total variability. So, as a result your table looks like this: population, error and total, then SSB, SSE and SST, and you have already seen that what is the degrees of freedom case, L minus 1 for SSB, for SSE NL minus L and for SST NL minus 1. This n multiplied by capital L, this is the capital N, what I have discussed earlier, that is the capital N. Okay. This capital N, this is n into L, but if you take unequal sample size, this is the different one. Okay. Now, what is MSB? MSB is mean squared between populations. This is nothing but sum square between population divided by its degrees of freedom. Okay. Then what will be your MSE? MSE is SSE by its degrees of freedom. So, this MSE will come here. You write like this, MSB is this, MSE here under error, you write under error MSE. So, I am writing again what will happen here, population, then error, then total. These are the sources of variation, sources. We are computing sum square, that is sum square between populations, sum square error and sum square total. What is our degree of freedom? Degree of freedom, it will be L minus 1, and this will be your n minus L, and this will be n minus 1, where n is nothing but capital L into small n. And then we are talking about MS, mean square, which is SSB by n minus L minus 1, and this will be MS SSE by n minus L. So, that means what is this? SSB by L minus 1 is MSB, SSE by n minus L is MSE. Okay. Now, you are finding out a statistics called F, which is MSB divided by MSE. Why it is F distributed? Ratio of two chi-square variable, because SSB is the square, this is sum square and sum square, ratio of two square, this is F distributed. Okay. And what will be the degrees of numerator and denominator degrees of freedom for F here? Definitely what is there in numerator? SSB by degrees of freedom L minus 1. So, we will be comparing this with L minus 1, and what is the denominator degrees of freedom? N minus L, and you will find out certain value of alpha, and if your computed F, that F computed here is greater than F L minus 1 n minus L into alpha, you will reject the null hypothesis. Okay. So, once you reject null hypothesis, you will accept the alternate hypothesis, that is the issue. The problem, in the same problem we have done the hypothesis testing, and population, that variability sum square between population is 43.415, error SSE is 25.686 and total is 69.101. Degrees of freedom, because there are 3 processes. So, 3 minus 1, that is 2, 3 minus 1 is 2, and there are 30 total observations, that minus 1 is 29, and the difference between 29 and 2 is 27, that will be definitely the error degrees of freedom. Then mean square is 43.415 by 2, that is 21.708, and for error, that is again 25.686 by 27, which is 0.951. You see the mean square value is very less. It is so less because there is effect. So, then F is MSE by MSB by MSE. This is 21.708 is MSB and 0.951 is MSE, and that ratio is 22.82, and which is far away from 0, which is far away from 0. If you see the F table, you will find the probability is almost close to 0. That means, if I say like this is my F distribution, that means you are somewhere here, this one, which is your 22.82. This one is close to 0. So, there is difference. This is what is tested through grossly tested through ANOVA. First level test is this, there is difference in population, our this one, the means, population means, that is what you are testing. Okay.
Any two population, any two means there is a difference between any two population.
No, but here when you test this F test, when you are doing here, your now what is your null hypothesis? Null hypothesis, no population, no differences in population means, correct. What is the alternative hypothesis? At least one pair is different. So, when you complete this one and if you find that you are rejecting H0, it simply says that there is population difference in terms of population means, but you do not know which pair. So, we have to know which pair are different. Okay. So, next class I will explain this, which pair is different and other things.